All right, everybody, let's get started. We've got a lot to go through today. We want to stay on track. Remember, we stopped in 7.3. So you can kind of see the title screen. So you remember where we're at. Central limits theorem with proportions. Okay, so we're learning about central limit theorem. Okay. Then we did central limit theorem with means. Now we're doing central limit theorem with proportions. Okay. These are very important to understand because as we move forward into chapter 8 today, which I'm going to finish up this one really quick. Chapter 8 is pretty long. Okay. Chapter 8, we literally start statistics. Okay. No longer will we be dealing with populations at all. Okay. Let me kind of come down here to where I left off. This is roughly where we left off the other day. As a quick review, remember central limit theorem says that as long as I take a sufficiently large enough sample of something, then I can say that regardless of what kind of distribution the population has, I know that my sample is going to approximate a normal curve. Okay. Well, with proportions though, you don't really look at it that way. We got to look at it more this way where we say, hey, we're not looking at it at 30 like we would with means, but here, just like we do with the binomial theorem, we look at it where NP has to be greater than 10 and the other one has to be greater than 10. Okay, kind of a hint on your final. Don't worry about it. They're always going to be greater than 10. Okay, on your homework. Okay, so sometimes you may do a lot of math and find out that you didn't have a large enough sample. Okay, so kind of be aware of that. Realize though, okay, just like earlier, when the mean, remember the mean earlier, and when we did sample means, the mean of the sample is the same as the mean. Okay, well, this one's going to work out the same way. Look here. The mean of that p hat is the same thing as the proportion. So when they give you a proportion, that's your mean. We're going to do an example and it'll make a lot more sense. Okay. And then this right here is going to be how you get your standard deviation now. You're going to have to remember that because your calculator doesn't do it for you. Okay. You're going to be given this information on your final. You'll get a list of formulas, but remember, you got about 3 different definitions of how to get a standard deviation right now. Okay. And you're going to have to be able to pick and choose which one you need to use at a certain time. Now, once you find your standard deviation, you do have your normal CDF button that can go in there and find your area and stuff like that. But you've still got to be able to parse out this information yourself. Okay. Good so far. If you decide, okay, hence the word decide, to standardize. That's how you would standardize it. Okay. Remember, you don't have to standardize. Okay. You need to understand what standardization says. Remember, standardizing is saying I'm taking a piece of data, right? And instead of using that data point, like say 43, I'm going to plug it in with the mean and I'm going to turn that into a z-score. Okay. And when I standardize it, obviously that will turn the mean into what? When you standardize it, what's the mean become? Mean? 0. The mean becomes 0. The standard deviation becomes what? The 1. Okay. So that's when you standardize. If you decide to use your table, okay, remember the table's in your book. Did anybody bring their book today? Okay, you're going to have to start bringing your book. Because in chapter 8, there's going to be things you have to use in your book. Okay. So FYI about that. I'll give you those tables on the final, but until then, you're gonna have to use them. There's no way to do them on your calculator. There's no way to get them any other way, but that's for chapter 8. So I'm kind of getting you ready right now. And if you don't want to bring your book, print it off. Print off the table, bring the papers. Then you don't have to carry a whole book around. Okay. So kind of make it easy on yourself. So let's look at an example here. Suppose 57% of the students in a university are baseball players. Now, I made fun of this one yesterday. Use your information just that you have in your God-given brains. Why does that sound weird? 57% of the students in a university are baseball players. That's a crap ton of baseball players. Okay, because look, they just took a sample. If a sample of 564 students, is that all the students? No, that's a sample of 564 students. So let's just say there's only 565 students in that school. That means that's a baseball team of 200 plus baseball players. I think our baseball team has like 20. Okay, I think in the whole MLB, there's probably like 200 in some of our players. So that means no, we just kind of, one student brought that up. I was like, that is so true. That's an abnormally large amount of baseball players. So anyways, I digress. Sometimes these math books, I wonder if they were thinking about what they were using as an example when they wrote this. So I don't know. If a sample of 564 students is selected, what is the probability that the sample proportion of baseball players will be greater than 51%? Round your answer to 4 decimal places, obviously, because we're dealing with probability. So let's start putting this together. Now, I'm going to be honest with you right now. What you should do and get in the habit of doing, but for sake of time, I don't really have time to do that for you. When I update all the notes and lecture videos this weekend, then heck, bro, don't get food poisoning. I'm telling you, wreck the whole weekend. Okay. You need to do your NP, but this one's kind of obvious in a weird, come on, I got 564. My NP is probably going to be greater than 10. My N1 minus P probably going to be greater than 10. But you should go ahead and kind of get the habit of doing it, okay? But now let's start parsing everything else out. Now remember, you have a thing that says this. The U of the P hat is equal to the P. Well, what is that P? Remember, P is proportion. Proportions are percents. So what is that main P I'm looking for? Very good, 57%. Change it over into a decimal, okay? 0.5. Continuing on, okay? So if a sample of 554 students, that sounds to me like they just gave me an N, right? Little n, so that would be my little n right there, 564. And then you can go one of two directions. You can either say, hey, I'm going to sketch what I need to see, or realize I don't have a standard deviation. But they give me enough information to get a standard deviation, and I have a formula, okay? So we know to find this standard deviation of the P hat is going to be big square root, okay, of P 1 minus P all over N. Good so far? Okay. Can fill in the information there. I've got this 0.57, 1 minus 0.57. Close that off, 564. Now, I'll be honest on these. I know it tells me to round to the nearest 4 decimals, okay? Standard deviation, I've always just gone to 2. It's worked out just fine. These, and I do this in the notes, since I know things can get really weird with decimals sometimes I'll just keep this as a really kind of longish decimal. So I'll put 0.02084. But remember, when it's all said and done, I'm going to round my final answer to 4 decimal places, okay? So I do tend to keep a little bit longer decimal point. And now, I'm going to do my drawing. It says I've got, once again, because I know that my population probably does not approximate a normal distribution, but the central limit theorem tells me if I take a sufficiently large enough, sample, I can treat it like it's gonna be a normal curve. It's gonna approximate a normal curve. So let's treat it like one. I know that I have a mean, but my mean is actually gonna be that proportion of 0.57. And then it says greater than 51%. There's my little data point. So I'll put that, like say, right about there. So we'll say that's 0.51. And I'm looking for everything on that side. Am I correct? What button on the calculator mode do you think I'm about to use?
Normal CDF.
Exactly. Once again, the normal CDF again. And now I have all the information I need to put everything into my calculator. So I'm going to use my normal CDF button. I have a lower bound of 0.51. I have an upper of 1e to the 99. I have a mean of 0.57. And then that standard deviation I found 0.02084. As you're working this out, I want you to realize something. Unless you do like a just really, really exacting drawing, it's going to be hard for you to intuitively know if your number is correct. Now, I've seen people in these statistical videos sometimes I'll watch, and man, their little sketches, man, they are amazing. I'm like, God, you spent a lot of time on that drawing. I don't do that because I'm just worried that drawing helps me finding my lower and upper bounds, which way things are going, helps me see things, okay? So notice whenever you do the math to this, I'll put it right here. Did you get roughly 0.9980? So there's your answer. Notice the reason I say this is not really intuitive because does my drawing look like I have 99% of that colored in? No, but that's okay. I use my drawing specifically to help me. Where's my bounds? Where's everything going? Okay, so that's literally what you need to be using the drawing for. Okay. And to be honest, how is this any different than the mean now? When you learn how to do the mean, it kind of works the same way now. Okay. The only part, which I will kind of let you know now, start paying attention to the problems a little bit carefully, okay? They're all kind of worded, every chapter words them just a little bit different, so you kind of know where you're at, okay? Because like I said, we're really close to the final, okay? There is a review out there already. We probably will not have time for a review in class. So what I'm going to do with that review is I'm going to go back through and put down where you can find that problem, okay, in Hawks, okay? Because your final test will be in Hawks. Okay, so your questions will be randomized and they will be decided on Hawks on what level of difficulty it is. Okay, and then you'll still do the same thing as normal. I decided to pull it off canvas and put it straight directly in. Okay. You've done a lot of stuff in Hawks by now, so you're used to that. Okay, you'll still be given formula sheets. You'll still be given everything you need, tables, everything else. Okay. Even though Hawks does provide a lot of that for you. I've checked it, and it still will even in the test. Okay. The final test is 15 questions. Okay. Good on this one? Okay. I'm gonna skip a few. Remember, I'm gonna have notes. Well, there's already notes there. There's kind of crappy notes. It's before I got a better program. So I'm updating the notes, but there are notes there. It's just they're more PDF, like scanned PDFs. I'm like, those look so good. So I'm trying to update them, but they're there. They still work. They're gonna be the same thing. Okay, but let me do one more example and then we've got to get to 8-1. Okay. 8-1's pretty long, but I gotta get through it today. So that one. Yes, this is the one. Suppose 47% of the population has a college degree. If a random sample size of 460 is selected, what is the probability that the proportion of persons with a college degree will, oh, look, differ? Remember that from last class, that differ. Once you see that differ, things are changing for you just a little bit from the population proportion by more than 4%. Round your answer to 4 decimal places. Let's remember, I gave you some hints. I drew you two different little normal curves the other day. And I said, if this one, that is less than this one here is more than. Remember whenever you see that word differ? So being that we're dealing with more than, this is what my graph, or this is what my normal curve is going to look like, right? Things are outside of my bounds, okay? So let's parse out the information really, really quick, okay? And then I'm gonna give you I don't do it this way in the notes. I give you the other way, but I'm gonna give you a way that I think is a little easier, but really up to you. We have this U of, P is equal to what? P, which is equal to what?
0.47.
Exactly, 0.47. What is our N that we're looking for?
46.
Very good. And then we've got to find that standard deviation, which means I'm gonna have to come in here and start using that E 1 minus P all divided by N and take the square root of it, which means we need to be very careful with our calculator work, correct? Okay, start putting in all the information and I've got 0.47, 1 minus 0.47, all divided by 460. Do that, like I said, I keep it in a pretty long decimal. I get 0.02327. And I now have a decision to make. What's my lower, what's my upper? I'm using this one right here, right? But do I have to? Because I don't have any lowers and uppers yet. Okay, so you remember, you're doing something by differ. So you remember you got this 0.47. So even if I use this one here, well, let me just redraw it, take some time. I have this p-value of 0.47, but it says it differs. So no matter what, I still don't have anything here. Well, realize it says that 4% there. Okay, so you still got to come in here and do what? You still got to plus or minus 0.04 from that. And when you do, you get this 0.43, and then you also get a 0.51. And now I have some bounds. And while this is what I'm looking for, we change colors here. Go with me for a second. Don't you think it would be easier for me to do this? Well, okay, I'm gonna be honest. You can do it either way. You could come in here and say, hey, this is shooting off to negative infinity, and here is an upper, right? Or this could be a lower, and it's shooting off to positive infinity, right? And that could be the upper. And then whenever I found one of those areas, I could multiply it by what? 2. Or you could find the area of this and then do 1 minus. Because that would be the complement of it. So it's really up to you what you decide to do on whenever it says more than. When it says less than, you're kind of hemmed into doing it that way. But does everybody get what I just said on that one? There's a lot of different ways you can do it. Me, I'm gonna go ahead and do it the opposite way, where I'm gonna take the complement. I'm gonna come in here and go, okay, well, my lower is going to give me that 0.43. My upper is going to be the 0.51. I have the mean here at 0.47. I have that standard deviation of 0.02327. And I get 0.9153. Now I'm going to one more decimal place because remember my final answer is going to 4, but is that my answer? That's not the area I'm looking for. I'm actually looking for what? The complement of that, because I'm looking for the tails. So I hit 1 minus, hit answer, and then I get my actual answer of 0.0847. And there's your. Good on that? Yes.
I got 0.0856.
Did you do the multiply by 2 part?
I got the same.
I got the same too.
5, 6? Did you do the bounds or did you do the multiply by 2 part? That's why. I went bounded, kept it long. When you multiply by 2, you're gonna get just a little bit of difference at the very end there. So depending upon how you do it, yes, because whenever I actually do it, like if you actually look at my notes online, it's got the 0.0856 because I do the multiply by 2. Okay, you're gonna get some variances like that because of the exactness that you're gonna be able to get between compared to when you do the complement of it. Okay, so expect a little bit, and I offer about a 2% variance in answers sometimes because of that, even on test. Hawks may show it wrong. I'll be warning right now. I don't even release grades on the final until I actually put eyes on every single question, okay? To make sure, because you know, you've all taken chapter tests. How many times you put something in there and you're like, man, I put a space and it counted wrong. I go look at it. I make sure to look at every single question. Okay, so I'll take a look at that kind of stuff. Okay. Somebody else raise their hand back here somewhere. Are you good? All right, there's central limit theorem. You're gonna keep using these formulas. Okay? But now, at long last, I can finally say to you, welcome to statistics. Because you haven't done anything. What we've done now, what we've done before now in chapter 7 will say, hey, the reason statistics works is because of the central limit theorem. That's why it works all the time. Notice what this says. Estimating a population means sigma known. Sigma is our what? Well, soon we forget. Standard deviation. Okay? Gonna have to be very aware now because now probably 90% of your final questions are gonna come from this chapter on. And the questions are all gonna look eerily close, but you gotta start saying, what is it asking me? Okay? Do they give me a mean? No. Do they give me a standard deviation? Yes. Oh, okay, that's gonna be chapter 8.1. You kind of know where to go back to in your head. Okay? Because you're gonna see, we're gonna have what happens, how you're gonna estimate stuff when you don't know the standard deviation. Okay? Because think about it, to really know standard deviation, you gotta know the population. Well, that means this one right here isn't used a lot. Okay? Unless you're in a factory setting. Factory setting, I may not know the population, but I know the variance I want. So notice how that's why sigma might be known in those scenarios. Okay. So estimating population means sigma known. I know. Because this one gets murky quick, so you need to be paying attention. Okay, remember, major reason we're doing statistics is because we need to make informed decisions. We're going to start doing inferential statistics. Okay, remember, you're going to have to sometimes tell me, good thing is on Hawks, it's going to give you a lot of little, hey, this is what you're seeing, okay? But you have to be able to tell me, hey, this is what this is telling me now. What are you inferring about the population of what you just learned about the statistic you just took? Okay? Also, remember, we don't need statistics if we know the population. Okay? So every little formula you learned in chapter 7 is coming back now. Okay? You're gonna have to use stuff. So let's continue on. Point estimate. You need to remember this. A point estimate is a single number estimate of a population parameter. Okay? We also call it an unbiased estimator. Okay? An unbiased estimator is a point estimate that does not consistently underestimate or overestimate the population parameter. For us in this chapter, it's going to be the mean. In this chapter. Later on, in chapter 8.4, it's going to be the proportion, like what we just learned, right? In 8.5, it's going to be the variance. So notice, but it's all going to be the same thing. So point estimate, unbiased, means it's going to be basically that number that's going to be kind of in the middle. That's going to be the thing we're kind of looking for. It's a fixed number that we're going to be using. Okay, for us, our unbiased estimator for this chapter is now going to become X bar. You're not going to see mean anymore. You're no longer using mu. We don't know the population anymore. You have no idea about it. Okay, we are now taking samples. Okay, so remember, X bar is just the sample mean. Okay. So I'm not going to make you do this because it's for the sake of time, but hopefully every single one of you knows how to do this. If I said to you, find the best point estimate for the population mean of a test scores on a standardized biology final exam. There's all the test scores. How would you find the mean of all that? Or use your list function. Yeah, just put everything in your list, right? And then let it do the calculation for you, and it's going to give you the X bar in it. Okay? So yes, use your list function. Okay? Is it possible this could be a assessment question or final answer? No, too easy. So the X bar for this one is going to be 81.6. Simple enough, right? So you have a mean now. You have something you can say, hey, you know what? I'm dealing with a normal curve right now. I found a middle number. Okay? Now I need to make sure that whenever I take a sample, I take a sufficiently large enough sample, obviously. Now, an interval estimate. Okay. This is where students get lost. So you need to if you don't understand this, ask questions, email me, do something, or just go memorize the process. Okay, because every year this is where people get lost. You're now in margin of error land. Okay, an interval estimate is a range of possible values for a population parameter. The level of confidence denoted by C is the percentage of all possible samples of a given size that will produce interval estimates that contain the actual parameter. And that's a weird one. And then the confidence interval is an interval estimate associated with a certain level of confidence. Let me show you. I have a little example here. I have a population mean here of 68. I know it. You don't. But what happens is this. If I have a confidence level of 90%, which that would be my C, C is equal to 0.90. I'm saying that I am pretty confident, 90% confident, okay, that one of my samples, 1 out of 10 samples, okay, or actually let's put it 9 out of my 10 samples actually has the mean in it. Notice I take a sample. You're gonna learn what this interval is here shortly. But that's that interval it's talking about, that confidence interval, okay? I find my interval and is the actual mean inside the interval here? Look carefully, is it? If this is the mean right here, following along this line right here. Is it? Yeah, look, it's in there. And it is all the way until, look right there. At this sample, sample number 5, that interval did not contain the mean. Okay, but the rest did. You will never know the actual mean of the population. The population mean is a fixed number that you do not know because you do not know the population. Okay, so what you're doing is saying, I don't know the mean, but I want to have a 90% confidence level, 90%, that when I start taking samples, I can roughly say that the mean is between here and here. And you can go, how confident are you? I'm 90% confident. It fits between here. Could I be wrong? Yes. But at 90% confidence level, you can go, if I take enough samples, we can kind of see what's going on. Okay? Are you okay so far? Good news is, I'm going to show you how to find confidence intervals. And for those of you who refuse to bring your book, you get to do the math on it every day, and it's ugly. Or bring your book, and there's a nice little chart that gives you these numbers for free. Okay? So if you'll turn to the very front of your book, I'll show you here. It's gonna be right beside your tables. It's gonna be called levels of confidence. So let me kind of pull it in here. As you pull that up, I'm gonna keep going, then we'll get to it. Now, margin of error for maximum error of estimate. Everybody's heard, we just went through an election, you heard margin of error. They were saying so-and-so is winning by this many points with a margin of error of plus or minus 3. You've all heard that. Well, now we're doing margin of error. Margin of error is the largest possible distance, how it differs from the point estimate that a confidence interval will cover, okay? So you have this little point estimate here. For us right now, it's going to be our what? In this chapter, what is our point estimate?
It's a single number estimate.
Which is mean, which is,
X bar.
thank you. Very good, X bar, everybody was right in their own way. Put them all together and you're 100%. So notice you go this direction, you add the E. You go this direction, what do you think I'm gonna do? Subtract the E, exactly. And then I'm gonna get a lower point and I'm gonna get an upper point. And that right there is going to be my margin of error that I am creating. I'm gonna say, hey, I believe my mean is this. Okay, not really, I'm kind of lying to you. You don't ever actually really care about your point estimate anymore after that. After you find your margin of error, you're like, whatever. Here's my guy. Here's my distance. And then you kind of go, I think the actual mean is sitting in there. Okay. Everybody good so far? You found that in your book? You don't have, you have to use the, just get ready because I'm gonna use it. Did you find a little level of confidence thing there? Okay, good. So get ready for it in just a second. Let me show you here. A college student researching study habits collected data from a random sample of 250 college students on our campus, and it calculates that the sample mean is 15.7 hours per week. If the margin of error for her data using a 95% confidence level is E is equal to 0.6 hours, construct a 95% confidence interval for her data. Interpret your results. Okay. This one's easy because guess what you didn't have to find? You didn't have to go looking for E. They gave it to you right there. They said E is 0.6 hours. They also gave you the mean of 15.7. So I'm literally gonna come in here and go, okay, well, if my X bar is 15.7, my E is 0.6. Well, how do I find that? How do I find that margin? Can I do that? Add it and subtract it. So you come in here and you go 15.7 plus or minus 0.6. When you do that, okay, you're gonna get this, obviously. You get 15.1. And look at how I'm gonna write this. And you can write it either way. I believe, and I'm probably gonna get found out wrong. I think it's parentheses, but I'm gonna put parentheses right now, but maybe brackets. A student last semester, how come you don't remember numbers? I go, do you know how many numbers I do within a day? Realize, now what is that? What is that saying? Notice what it said, interpret your results. You tell me, I want you to walk away from this class. What is this saying? Why did I put the mu there? Is it? Do I know the mean? Do I know that population mean? No, I don't. I have no idea. But I am 95% confident. Okay? With that with that margin of error, that the population mean sits between 15.1 and 16.3 hours. Could I be wrong? Yes. But I'm 95% confident. Why am I so confident? See chapter 7. Because we've done central limit theorem. Because we know it works. Because it can be proved mathematically through formulas up to infinity. Now, can I be wrong? Yes. Could I have taken a sample and it be wrong? Yeah, that's why you sample again. And then you sample again. And you sample more. There's a lot of really, really good, I could name them off, I listen to them. There's a lot of really good like scientists out there talking right now. I'll name something like, how many of y'all heard of that Huberman guy? Peter Attia, all kinds of people. And they're really good about going, the scientific literature says, and I like it when they say that word, scientific literature, because they're saying more than one study, which my math brain says that means more than one sample. But whenever they say this, I was reading a study and it says this. That's when I kind of go, Because remember, that's why studies need to be replicated. Because of this level, this margin of error. What if that statistic I did was, what if my mean is outside of it? That kind of help y'all see why this needs to be replicated more and more and more. Okay? So we are 95% confident our actual mean is between 15.1 hours and 16.3. Hear me now. You will never know for sure. We are proving nothing. I want to say that now because we're going to get to hypothesis testing and it's going to say, oh, look, I proved the hypothesis wrong. You proved nothing. This is statistics. The more data, things change. Okay? So we are statistically thinking this, okay? But we don't know. Okay? Well, how do you find margin of error? Do you think I'm gonna be that nice to just give it to you every time? No. Nobody's that nice, not in a math class. So first off, we gotta make sure if we're gonna do this, we need to make sure some conditions are met, that all the samples have equal probability of being chosen, okay, and that a simple random sample is being used. Also, while reading your question, they're going to give you the standard deviation. So this kind of lets you know, oh, okay, I need to go back to 8.1. And, oh, lo and behold, look, the sample size is sufficiently large. Why does that matter? Didn't central limit theorem saying for central limit theorem to work, okay, when dealing with means, You gotta have enough samples for it to work, and for us, it's gonna be 30. Definition, critical Z values. Okay, we're doing great on time. Critical Z values denoted by negative Z alpha over 2 and Z alpha over 2. Mark the boundaries for the area under the middle of the standard normal curve that corresponds with a particular level of confidence C. That's a word salad, isn't it? Okay. So. This is gonna be why you're gonna want to should be very happy about all the old dead Germans that did all the math for you to these tables. Okay. Everybody good if I move on? You're gonna need about a minute? You okay for right now? Yes. Let me kind of come back here really fast here. Oh, let me show you that. There you go. Got some formulas. You need, well, okay, you kind of need to know it. Okay. But good news, you're gonna have to know the E. Okay, you have to know this guy right here. There is no button on your calculator for that. Your chart that I'm telling you about is right here. You see this guy there? That's what your chart's about to give you. So don't freak out about that. All you gotta do is look at your chart and that's gonna give you a number, okay? But I'm going to show you how they found that. Because you're good math students and you love math, that's why you decided to take another class above college algebra. Good on that? You got it written down?
What is the middle thing between Z and H? Is it just A?
Z and H,
Yeah, right there, or what is
that's
it?
alpha over 2. Everybody get that? I'll rewrite it again a little bit bigger here in a second. Let me see what they're saying. This is what it is. Okay, we're going to be using a confidence level of 95%. So 95%. If I have a standard normal curve and I put 2 bounds here, I can say that 95% of this area right there is colored in, right? I know that this area here is alpha. But I also know this area here is alpha. So if I wanted to find the area of that, it's alpha over 2, right? Over here would also be alpha over 2. Kind of make sense so far? Okay. Well, I'm looking for z-scores. That's why you saw that z. Remember how I kept telling you z-scores are going to be super important, and don't forget things about z-scores. They're here to stay forever and ever and ever. Why? I want to know that z-score there, that z-score there, which is why your formula says you're looking for a negative z alpha over 2 and a positive z alpha over 2. Are we good so far? Okay, well, let's think about this. I know to find alpha is going to be this, 1 minus C. Remember, C is equal to that right there, right? C is my level of confidence, which is going to turn into what? 1 minus 0.95, which is going to equal 0.05. But I have 2 tails, don't I? So I divide that by 2. And I get 0.025. Are you noticing any numbers now? You can kind of start probably seeing on your, if you look at your 95% confidence level on that little part of your table. Now look here. I come back in here, I've got a horrible normal curve. I'll draw a better one of these days. If they would make this where it would lay down, dude, I would be doing some like Rembrandt stuff, but this is like trying to do something on a balancing ball. I now know that this area here is 0.025. I also know this area here is 0.025. And man, I love normal curves because they're symmetrical. And when I have the area of something, but I don't have the Z curve, the Z score, don't I have a button on my calculator that says, hey, how about you use inverse norm, INV norm, 0.025, and I get negative 1.96. But I also know there's a positive form of that, and it's going to be 1.96. Now, do you see a 1.96 next to your 95% confidence level on your in your book? Look at 95%, look at the very bottom, it's gonna be a little bitty square. Yeah. So I just did it by hand. You don't have to. You now have, it's a little bitty square. Is it on the left or right-hand side? Right-hand side at the very bottom of the page right here, it has like level of confidence. So when they say 80% level of confidence, you just scroll right over there and go, there's my number I need to plug into the formula. When I'm using 95, look, you're using 1.96. The reason you need to know, you don't, but sometimes people aren't going to use something that's on that. Okay, so they have ways to figure out their own. But these are the most custom standard ones we're going to use. Okay. You good? So let's find a margin of error then. Let's actually do the math then. We're going to find margin of error. Remember, helping you how to pass. Check for sigma. Are you dealing with a population? No, you're dealing with samples. Look for words, okay? You got to start learning to parse out stuff, okay? Just because they say the word population doesn't mean you're dealing with a population. So be careful about that, okay? So let's look at this one. Researchers want to estimate the mean monthly electricity bill in a large urban area using a simple random sample of 100 households. Let's stop right there. Have they missed some conditions already? Remember I said we have to meet some conditions for this thing to work. One, simple random sample. How many samples do I need to have? Minimum. 30. 30. How many do I got? Man, we're looking good so far, right? And then also everything has to be done the same way, okay? Assume the population standard deviation is known. Oh, hear that word? Known. In my mind, if I was doing the final, I'd be like reading this going, okay, which one population standard deviation 8.1. That's where I'm going. Okay? Because they're giving it to me, because eventually I'm not going to give it to you. Okay? It's known to be $15.50. Okay, so that's the population standard deviation is known to be $15.50. Find the margin of error for a 99% confidence interval. That means you want to be 99% confident that your mean is in there, right? Okay, so let's figure it out. We have E. Well, we need to find E. And E is going to be, you take your Z alpha over 2 and multiply it by your standard deviation divided by the square root of n. So what would be that Z alpha over 2 for a 99% confidence interval? Would you like to do the math or would you like to use your book? Very good, 2.575. So I'm going to come here and say 2.575 times, now they give me a standard deviation, don't they? Of $15.50. We also have samples. And what do you get? Get that? So what is our margin of error? Did you get to 399? So what is our margin of error? I'll put MOE. Plus or minus. Okay, isn't it? When you hear margin of error, you should be like, okay, think about back to the election. When they would say something like Biden's ahead, right? And then they go, Biden's ahead by 10 points. Well, what would they always say right after that? Plus or minus. This right here, whatever margin of error, that means behind the scenes, and you could go look up all this stuff. What level of confidence did they want? Were they all using, was a certain poll using the same level of confidence? If CNN was using the 80% level, if Fox was using 95, or vice versa. Okay, and don't think one is better than the other. Do not think that 80% is better than 95%. You're gonna learn pretty quickly. There are inherent problems with both. The higher the confidence level, there's another problem creeping up behind it. Okay, and they're called type 1 and type 2 problems. Okay. And it just depends. Like when one thing goes low, the other problem goes up. When one thing goes this way, the other thing goes up. Okay. So yes, our margin of error is plus or minus 3.9. Let's put it all together. Let's put everything together so you can see how it works and how it's going to keep working from now on. Okay? The owners of a local company that produces hand knitted hats want to know the average head circumference for adults in their area. Well, I need to write a statistics book. Sorry. There's a terrorist problem in here. I've been trying to find it in the book. There's like a myth of a terrorist problem. You know, and I've been trying to find it. So if y'all see something about terrorists, let me know, like email and go, I found it. Okay. I might even give you like a bonus point or something like that. There you go. Toss that out to the fish and see what happens. Okay. They collect data from 431 randomly selected adults. That's kind of important, random, right? The sample mean is found to be, oh, look, they gave us a mean. Did they give us a mean last time?
No.
No. The sample mean is found to be 24.3 inches. Construct a 95% confidence interval for the mean head circumference of an adult in the company's area. Assume the owners know the population standard deviation is 0.36 inches. Okay. Well, let's start taking some information here. First off, do we know they're in?
Yes,
And it is what?
for 31.
And that's nice because it is greater than or equal to 30. That's always nice because we need that, right? Okay, do we have our confidence interval? What is that? 95%, right? Okay, 95%, which means I'm gonna need to have what is that number gonna be? And we worked that out earlier. Well, you'll probably remember 1.96 forever now, okay? So 1.96. Do we have a mean now, though? What is it? Exactly, 24.3. Do they know the population, though? No, they just know a sample. They took a sample and they go, this is the mean head size we found. Okay? Do they know a standard deviation? Yes. Somehow they know a population standard deviation of the head. I don't know how that happened, but they do. They know it. Okay? So they do have a standard deviation here, and that is what? Yes. 0.36. We need to find our E. Okay, we need to find our margin of error. So let's come in here. E, which is equal to Z alpha over 2 times our standard deviation divided by the square root of n. Well, we've got all that information. Let's go and put everything in here and go, okay, well, I've got 1.96 times what? 0.36. What's our N? 431. How about 0.03? That sound good? Am I done? So I just need to go like plus or minus 0.03 and I'm good?
No.
No. What am I doing now? What are we constructing? We have an interval now. We have all the information to say, oh, we have an interval. We have our mean, okay, which is 24.3. And we're gonna plus or minus that 0.03 from that. So we come up with an interval that says this. 24.27 inches. What is that saying though? I don't want you just doing math. What is that saying to you?
That the mean could lie between those two.
You could what?
That the mean could lie between those two.
How confident are we?
95%.
Does it mean could it really be, is it in there though? Do you know that for a fact? No. But you have a level of confidence you're willing to stick with and go, hey, here it is. Here's my interval. I found my margin of error because I know the level of confidence I want. Okay? I know the level of confidence my business is willing for me to do. Okay? And so therefore I can tell my boss, hey guy, if we can make sizes between here and here, I think we're gonna be hitting the majority of what? The population in that area. That kind of help you kind of see it, put a little bit more of a story to it a little bit, okay? Now, let me pull up something real quick here. Just 2 seconds, please. Oh, that's trouble finding it. Because I'm blind. That. You want good news? Or you want bad news? Give calculation. Hit your stat key. Scroll to test. And go to Z interval. And then make sure stats is highlighted. If you're in the TI 84, it should be giving you a standard deviation, an X bar, an N, and then a confidence level and a calculate. I think on 83s, does it give you the same thing on 83 if you go to Z interval? If not, give me a professor, we can look it over. Okay, and notice you have a way to put everything into your calculator. Okay, you need to be careful with it on your calculator. Okay. So notice on this one, you can say the standard deviation, you can put it in of 0.03. Perfect, let me back out of this and I'll pull up my calculator. I'm just gonna use my notes real fast so you can kind of see it. So this can also make it to video today. Yeah. I'll go back. All right. Stat key. Go over to test. Go down to Z interval number 7, hit enter. Make sure you hit stats and hit enter here, okay? It's gonna show up on data first. Scroll over, make sure you hit stats. Are you good? These ugly faces. Okay, start putting in the information that you found. Okay, so notice they gave us, well, we found, they gave us a standard deviation, okay? But we had to calculate our standard deviation, didn't we? Okay. So we go in there and we calculate this standard deviation, okay, and it's going to be 0.01734, or you can put in your formula. Okay, that works sometimes. I never trusted it. I'm not that good with it. I'm like, nope, not gonna do it. What's your X bar? 24.3. How many? 431, and then what's my confidence level? C level of 95%. Hit calculate. There you go. Look up there at the very top. 24.298, 24.302. It is going to be more accurate. It is calculating to infinite decimal places. So if you do it on your calculator, it's still going to be correct. So don't worry about it. Okay.
I thought our standard deviation was 0.36.
That's the standard deviation they gave you. But I give you a formula for standard deviation. Remember, that's a standard deviation divided by the square root of n. That's the standard deviation you have to be using. That kind of help you see the little difference there. Okay, so be real careful with that. Okay. Good. So you got a way to do it on your calculator. Okay, it's kind of nice. Really up to you if you want to use a calculator. I mean, it's one of those, I'll be honest, I got so used to doing the formula that I forgot about the calculator after a while. Okay, but it's really up to you, whichever you want to use. Good. All right, let's finish off. Minimum sample size. Oh, look, that's always fun. The minimum sample size required for estimating a population mean at a given level of confidence with a particular margin of error is given by n is equal to z alpha over 2 divided by, multiplied by your standard deviation divided by your margin of, your margin of error. All of that squared. And do you want to know where I mess up the most on this one? I always forget to square it. And I get mad. I'm like, oh, right. So this is the formula. Whenever they say, hey, you know what? We took a poll of New Mexicans and we did a poll of 1,000 people in New Mexico. We've said that this many people are going to do this. And then you have those people out there and go, how do they know that's enough? There you go. This is your guy. This says, if I want this level of confidence, what's the minimum sample size I need to take to be that confident? So when you hear them say, we only polled 1,000 people, you can go see, did they use this formula? Sometimes they don't. I'm not gonna lie. Sometimes they're just some jackwagon sitting in some news station going, for 2,000 people, that's okay. So, but this is how it is right here. So we're going to use our n. Okay. That's going to be z alpha over 2 times our standard deviation, all divided by that level of confidence, all raised to the power 2. Determine the minimum sample size needed if we wish to be 90% confident that the sample mean is within 2 units of the population mean. An estimate for the population standard deviation of 8.4 is available from a previous study. Okay. Well, notice hey, what's my 95, what's my Z alpha over two? What is it for 90%?
Wait, 645?
Exactly, 1.645. Okay, do they give me a standard deviation? Was it? Do they give me an e-value? They did. Okay. So notice we can put all this into our formula. So let's come in here and go, my N is gonna be equal to, put your parentheses of, so a little parentheses in here, I've got 1.645 times 8.4, all divided by 2. And then I'm gonna square that whole thing and always round up to the next integer. Okay, always. You don't give decimals, you always round up. So notice when you do this here, you get 47.73, but how many do I actually have? 48. So the minimum sample size I need to take to be 90% confident from a population is only 48 people. That's not a lot. Here, huh? You expect it to be a lot more. Okay. How you feel about that? That's 8.1. I've got homework problems on there, okay, very first one. But after this. Yeah, it's pretty much just what we're going to be doing. Now, the next class, I'll be honest. This one is when it's gonna get a little bit weird just for a split second because I have to show you a new type of distribution. It's still gonna be a normal, but now we're gonna get into what happens if you don't know standard deviation. That's the majority of everything, okay? And it was learned to us by a drunk. Okay, so I'll see you all next class.
So that we.
I can see this.